Continuing with sections 2.6 and 3.6, derivative of trigonometric functions. So far, we used our limit identities to prove two things. One was derivative of sine of x is equal to cosine of x. The other was derivative of cosine of x is equal to negative sine of x. Now, using these two, we can prove, and a quotient rule, we can prove derivative of tangent of x is equal to secant squared x, and derivative of cotangent of x is equal to negative cosecant squared x. So this is using 1, 2, and so 1 and 2 and quotient. Then we can use again 1 and 2 and power rule, generalized power rule, to prove that derivative of secant x is equal to secant of x, tangent of x, and derivative of cosecant of x is negative cosecant of x, and times cotangent of x. So this time, what is important is all these rules also to prove the set, the cyan and the red set. What we need to do also is to use Pythagorean identities. Before getting to showing a couple of these, it's worth mentioning there are two sets of, if you see, we divided all the derivatives into two sets, right in the middle, and they are in each function, each trigonometric function, and its co-function. So, for example, derivative of sine of x is cosine of x, and then the co-function of sine of x is cosine of x. So derivative of cosine of x is equal to negative sine of x. There's a similarity. Derivative of sine of x is its co-function. Derivative of cosine function is negative of its co-function. How about tangent of x? Derivative of tangent of x is secant of x, and derivative of cotangent of x, which is the sister, which is the co-function of tangent of x, is negative cosecant of x, which now, if you know this, these two are cosecant of x and secant of x are co-functions. So secant tangent of x, if the derivative of it is secant squared of x, then cotangent of x, derivative of it is negative cosecant squared x. How about derivative of secant secant of x and cosecant of x? They're co-functions again, and one is secant of x, tangent of x. The other one is cosecant of x, cotangent of x, which again, they are co-functions, but with a negative sign. So basically, if I learn the set on the right, on the left, then I can assume that all the co-functions in there are going to have the co-function derivative to these with a negative sign. So we have to memorize all these derivatives: sine of x, cosine of x, tangent of x, cotangent of x, secant of x, cosecant of x. But let's try to also use the use a derivation method to If we forget some of them, we can remember. So let's start with derivative of tangent of x. What is tangent of x? It's sine of x over cosine of x. And when you're taking derivative of sine of x over cosine of x, you use a quotient rule. And so when you're using the quotient rule, it would be cosine of x, which is the denominator, times derivative of sine of x, then minus sine of x times derivative of cosine of x, and divided by cosine squared x. Now, what you get out of derivative of sine of x is going to be cosine of x, so the first term is going to be cosine squared x. The derivative of cosine of x is negative sine of x. Therefore, the second term, so here, this one, is negative sine of x, and this one is cosine of x. So negative sine of x and cosine of x, so you get cosine squared x plus sine squared x over cosine squared x. Now, what is sine of x plus sine squared x plus cosine squared x? That's equal to 1. So what you end up with is 1 over cosine squared x, which is 1 over cosine of x is secant of x, so this is secant squared x. We just proved that derivative of tangent of x is secant squared x. Now let's show that derivative of secant of x is secant of x tangent of x. So here, what is secant of x? That's cosine of x to the power negative 1. A generalized power rule gives me negative 1 times, that's a chain rule, right? Negative 1 times cosine of x to the power negative 2, that is u to the power negative 2, times derivative of u. And that would be derivative of cosine of x. What is derivative of cosine of x? That's negative sine of x. So you have negative sine of x over negative cosine of x, cosine squared x. And this, I can use some identity to, some algebra to put sine of x over cosine of x and multiply it by 1 over cosine of x. So it looks like this. The fraction hasn't changed, it's just the product of two fractions now. And the first one is secant of x, the second one is tangent of x. And we just proved derivative of secant of x is secant of x and times tangent of x. Derivation of the derivatives of cosecant of x and cotangent of x are very similar, and you get the cofunctions of the derivative of secant of x and tangent of x with a negative sign. Now let's do a few examples of derivative of trig functions. First example, find the derivative of cosine of e to the power tangent of x. So first step is, here we have a most outer function, which is cosine of x, and we have an inner function that is e to the power tangent of x. So first we take the derivative of the most outer function, which is going to be minus sine of, and then in big parentheses put everything else. So I'm putting e to the power tangent of x. See, I didn't change anything. Now, and the next step is to take the derivative of e to the power tangent of x. And so this time around, I know that derivative of the outer function is the exponential. So I will get the exponential and then to power the inner function unchanged. The inner function of this part is tangent of x. Then I have to have the derivative of tangent of x. Derivative of tangent of x is going to be the secant squared x. So it's sort of a peeling layers of onion. First you go very outer one and you come up with a negative sign of something, and then you plug in that something, which is, we say negative sign of u, and then u will be basically tangent of x. And then e to the power tangent of x. Then you take the derivative of that u, and that u has layers also. So another chain rule for e to the power tangent of x. And then after that, you basically, what you end up with is e to the power tangent of x, and then derivative of tangent of x, which is the most inner, and that would be the secant squared x. What's the derivative of secant squared 4x? And there is a most outer layer. The most outer layer is the to power. It's the generalized power rule. So peel that one down, it would be 2 secant to power 2 minus 1 of 4x. Now what was inside the power 2? It was secant of 4x to power 2. So the inner function was itself a composition of secant of x, secant of u, and 4x. And so now derivative of secant of something is going to be equal to secant of that thing, tangent of that thing. Then derivative of 4, which is the most inner, is going to, the 4x, which is the most inner, is going to be 4 times 4. But what was inside? It was 4x. Then if you multiply the 4 and the 2, it become 8, and then there was a secant in the beginning and secant later, secant of 4x and secant of 4x in the beginning and end, and they become together secant squared 4x. Now the next step, find the derivative of sine squared 4x plus cosine squared 4x. This one is very easy. I don't need to do the chain rule. Why? Because I know that sine squared plus cosine squared together of the same angle, sine squared of an angle plus cosine squared of the same angle is equal to 1. And so derivative of 1 is equal to 0. Could I have done it through chain rule? Yes, even though it's the lengthier work to do and really reasonably not needed, you could have done the chain rule. Remember, sine squared 4x, very outside function to power 2. It's so when you take the derivative of very outside function, it's 2 sine of 4x. Then you take the derivative of the intermediate inside function, which is sine of 4x, and that would be cosine of 4x. Then very inside function is 4, and same thing is 2 cosine of 4x times negative sine of 4x times another 4, which makes it 8. And if you look carefully, you see that they are they have all the same values. One is positive, one is negative. So when that means that this entire thing is the negative of this entire thing. So they cancel out and they become 0. And this was also, we could have just said it through using Pythagorean theorem, or we can do it the other way around using the identities. Of course, Pythagorean theorem is the best, but I did this part so you can practice a little bit with derivatives of trigonometric functions. By the way, a lot of times in our course, you see derivative of trigonometric function that can be simplified using the trig identities. Last but not least, example 1, part 4. How do we take the derivative of take the second derivative of sine of x? So the first derivative of sine of x is equal to cosine of x. So if I take the derivative of cosine of x, I get the answer for this one. And that would be negative sine of x. And so we're concluding this example. I click here question 1. The fourth derivative of cosine of x is option 1, and sine of x. Option B, cosine of x. Option C, negative sine of x. Option D, negative cosine of x. Option E, equal to 0. So pause the video and answer. When we're talking about derivative of cosine of x, so we start with cosine of x and then take the derivative and you end up with negative sine of x. Take another derivative and that is negative cosine of x, and another derivative from negative cosine of x, and you end up with sine of x, and one more, that's the fourth one, and you end up with cosine of x. So after 4 derivatives, you ended up with the same function as you started by cosine of x, and you took 4 derivatives and then you end up with the same function, and that's option B. Next, I click here question. I click here question 2. The question is asking the 30th derivative of sine of x is option A, sine of x, B, cosine of x, C, negative sine of x, D, negative cosine of x, and E, 0. And so pause the video and come back. So here, how do I find the 30th derivative? Let's say the first derivative of sine of x is cosine of x, and then we have negative sine of x, then we have cosine of x, then we have negative cosine of x, then we have sine of x. Fifth derivative again is going to be cosine of x. Sixth derivative is going to be negative sine. Seventh derivative, negative cosine. Eighth derivative is going to be sine of x. And so in any multiple of 4 is going to be sine of x. Any derivative whose remainder by 4 is 1 is going to be cosine of x. Any derivative whose remainder by 2 is going to be negative sine of x. By 4 is 2, and any derivative whose remainder by 4 is 3 is going to be negative cosine of x. 30th derivative, its remainder by 4 is 2. So we're looking at negative sine of x, and C is the